Hello, this is my lab report for Physics 2211 section N07. In this lab, I dropped a crumpled piece of paper from rest. Unlike the previous lab, the net force acting on this object is not zero. The net force is equal to the weight force, which is mass times the gravity constant, which is 9.8 meters per second squared, multiplied by the drag force, which is some constant times the opposite of the velocity squared. Using Newton's second law, I was able to track and make a model of the motion of the falling object. Here is my original video. After filming this video, I put it in Tracker to record its motion and extract that data. Here we can see the data recorded from Tracker, in this table right here, in the graph of that data. Next, I made a model of the motion of a falling object in VPython. Here we can see the initial conditions in this part, in this part, and this part. And here we can see the input of the physics concept, Newton's second law. However, this concept is flawed. In this picture right here, the net force does not account for drag force, assuming the object falls further than usual. That problem is fixed in the next model. In this model, drag is accounted for and the graph is more accurate. Here's the drag force, which equals the magnitude of the velocity squared. When running this model, we can see two arrows that account for the forces. The yellow arrow is a force of gravity, while the blue arrow is a drag force. Here, we can see all graphs together. The red line is the model with drag, the yellow line is the model without drag, and the blue dots are the experimental values. As you can see, the model with drag is different than both models. This is because the drag force acts oppositely than the downward velocity and causes the ball to move slower. The experimental graph is not the same as the model graph because of the errors in this experiment. The main cause for error in this experiment is the fact that the ping pong ball is not tracked well in Tracker. This is caused by poor lighting and a time scale that was moving too fast. This could have been corrected by changing the lighting and slowing down the video. Questions that need to be addressed. The first question is, does either model predict terminal velocity? Terminal velocity is reached when an object reaches a resistance moving downward that prevents any further acceleration. The model with drag included should predict terminal velocity. This is because the graph of the model with drag, that graph slope starts to remain constant, indicating a steady derivative of velocity, which is acceleration. Therefore, the acceleration should become constant. The second question that needs to be addressed is, would the terminal velocity be different if the object was initially thrown downward? The answer is no. The object would have the same terminal velocity. After release, in both cases, the object has all the same forces acting on it. The only difference between the two would be the starting velocity. So, the object would reach terminal velocity sooner, but because after the release all other variables would be the same, in both cases the object would achieve the same terminal velocity. That concludes my lab. Thank you for watching.